Okay, so our next reaction that we're going to be talking about is the acid-base reaction. Okay, so in the case of the acid-base reaction, we have to first define what an acid is. So an acid basically is a substance that when it's dissolved in water is going to give us the H plus or the H3O plus, which is the hydronium ion. So a strong acid is going to be one that dissociates completely, right? So as soon as you stick it in water, it's going to break up into its ionic components. So for instance, can you guys see my screen?
Yeah.
Good. So for instance, if we have, let's see, it's over here, so I'll be able to check to make sure that when other people are coming in, they're here. Okay. Hydrochloric acid, HCl. So hydrochloric acid, as soon as we stick it into solution or it's in water, it separates into its ionic components, which is Cl and the hydronium ion. Okay. And so since this is a complete reaction, we're going to use that yield arrow, right? Now, if the acid is a weak acid, the majority of the species are going to still be stuck together. So let me show you an example of that. First, let's skip through. First off, these are strong acids. So hydroboric acid, hydrochloric acid, hydroiodonic acid, nitric acid, perchloric acid, sulfuric acid. So basically, anything that has an ick at the end, except those that have carbon, like acetic acid. Acetic acid is a weak acid. So all carbon-based acids are going to be weak acids. Okay. If it has an OUS acid, so like sulfurous acid, phosphorus acid, all of those are also weak acids. Okay, so that basically means strong acids are going to separate completely into the ions, and weak acids aren't. They're going to get a partial separation. Okay, so let me show you what I mean. So in the case of a weak acid, the majority of the species is going to stay together. So here's acetic acid, carbon-based acid. It's a weak acid. So when we put in solution, you're going to have more of this guy present and a little bit of this guy. So you're going to get a partial separation. And this double arrow here, this basically means it has two meanings. One of the meanings is that the solution is in equilibrium. It found the point where you have the existence of both species existing at the same time. Okay, so in this case, you have very little of this guy and a whole bunch of this guy, but you do have this guy present. So you have your products. Oops. So this is acetate. So you'll have your acetate ion and your hydronium ion present, but it's going to be in low numbers compared to your acetic acid. Do you guys kind of get that?
What do you mean low?
So if we did percentage wise, right? So we'd say this would be like 90% this, and then 10% this. Okay, so that's what I mean by low numbers. So you have it present in solution, it's going to exist, but the majority of the species isn't going to separate. So you're not going to get this reaction, where in the case of like HCl, and rather than putting water with it, we're just going to roll it into the aqueous. You're just going to get your hydronium ion. Got to stop being lazy.
How does that work that a weaker acid is What is it? What was I gonna say? What was I gonna say? Gosh damn it! I'll come back to it.
Okay.
No, my question.
I'm going to start calling you grandpa here soon.
The dementia is hitting pretty quick at this age already.
Them early 20s, huh?
Yeah.
Okay, so like in the case of hydrochloric acid, you're getting complete separation. And you see that the yield arrow just shows you that you're getting that complete separation. But you don't have that partial existence.
So when
Okay.
you have both arrows pointing like that, it means that it's partial separation.
It means that you have both existing, right? But weak acids, if we know that it's a weak acid, that means that the majority of the species are going to be this. So this will be your major species over here. And then this will be your minor species, because there's like, I'm giving you a rough estimate. 90% of it is going to be in the acetic acid. And then 10% of it is going to be broken down to your acetate and your hydronium ion. Okay, are you guys picking it up? You kind of get it, the idea?
Yeah, kind of.
Yeah.
Okay.
So in each reaction, there's always going to be a strong and weak acid?
Not necessarily, no. You could have a weak acid and a weak base interact. Or you could have a strong acid and a weak base.
Okay.
Or a strong base and a weak acid. So right now, this is just showing you this here is the acid. And it just shows you that it separates. And in all honesty, you could write it as this. You don't need to have the water there because you already have the water in that aqueous part, right? And it's going to break down into these ionic forms. Often, the way that we write it to make it simple so we can keep track of those H's, we just write it as H+, which is also the hydronium ion. And we put AQ around it. Okay, so these guys are interchangeable. So you'll see some text will actually use this instead of using the hydronium ion. Okay, does that answer your question and make it clear?
Yeah, thank you.
So again, let me give you some examples of weak acids. So chlorous acid. This is one of the exceptions. Hydrofluoric acid is a weak acid. So this guy is an exception. The reason why it doesn't want to separate is because the characteristics of fluorine. Fluorine is very electronegative, and so it really likes to keep hydrogen at bay. Until it has an opportunity to find something that's better than hydrogen, it's not going to let go. It's going to keep it tight to it. Fluorine is kind of like that abusive boyfriend that won't let his girlfriend get away. You know, she can't go to the bathroom by herself, you know, or anything like that. He either has to send somebody he knows with her or he goes with her, you know. Okay, so that is an example, one of the exceptions. Usually anything else that has ick is going to be a strong acid. Like chloric acid is a strong acid. Bromic acid is a strong acid. Hydrobromic acid is a strong acid. Okay? And then I told you any acids with carbon are weak acids. Carbonic acid. Acetic acid. Ascorbic acid. So all of those guys are weak acids. Okay?
Mm-hmm.
And so when you're writing them and you see them with the double arrows, that's usually a sign that they're weak acids. And they exist in what we call equilibrium, meaning that they come to a point where you have both your products and your reactants existing in the same solution. Where this guy says you only have your products. Okay? Okay, so bases. So a base is basically a substance when it's dissolved in water, it's going to yield the hydroxide ion. So the OH minus ion. Okay, so these, the most common bases are going to have either the alkali metal or alkaline metals attached to them. So they're going to have the ions associated with that. So we have the sodium ion. So this guy, sodium hydroxide, potassium hydroxide, calcium hydroxide, barium hydroxide. Now, these bases are strong bases. So as soon as you stick them in water, they're going to dissociate. Okay. And so when they dissociate, you're going to get your sodium ion, and you're going to get your hydroxide ion. And again, you notice the complete yield, that yield sign, so it means it's going to be completely happening, complete dissociation. So, as with acid, there are weak bases. So ammonium is a weak base. So when ammonia is a weak base. So when ammonia is put in water, you're going to end up with ammonium and hydroxide. And again, you're only going to get a partial reaction. It's not going to be complete. So you're going to have the majority of the species is going to be in this form and only a little bit in that form. Okay, so ammonia is commonly used in agriculture. It's used for cleaning. So it's something that we use quite a bit, you know. Raphael, do you guys use ammonia in the field?
Yeah, you usually clean the tanks with ammonia when they use strong herbicides.
Okay. So do you also use it as a fertilizer, providing
Yeah.
as a nitrogen source?
Yeah, also as a nitrogen source. Usually in almonds too.
Yep. Okay, so when you have a neutralization reaction, that's when you have, and it's also called an acid-base reaction. So it's when you have enough acid to match up with the amount of base that you have, that you end up with a salt and water. So if you have a strong acid and a strong base that comes together, you're going to end up with a salt, meaning a ionic compound, and water. Okay, and here they give you an example. So if you have magnesium hydroxide and we add hydrochloric acid, what's going to yield? We're going to have magnesium chloride and water. Piece of cake?
Mm.
So let's see if I have. Oops. Did you guys have to update your Zoom? Do you guys have a Zoom app on your computer? Or do you guys always just go to the?
Oh yeah, I have that.
Yeah, ever since I updated, it does not behave the way it's supposed to.
Bugs.
Yeah. Okay, so for instance, if we have sulfuric acid and sodium hydroxide, all you're doing is, again, it's kind of like whether you look at it like this or not, you're changing partners. The hydrogen is acting like an ion, so it's like an H+. So that's going to pair up with the hydroxide. Let's balance it. And then the sulfate here is going to pair up with the sodium. Okay, so then if you see HOH, you know that's water, right? So you need to just rearrange it to H2O. Right? So that's essentially what you're going to get. You're going to get water, and then you're going to get sodium sulfate. Okay, and sodium sulfate will be your salt. Is that going to be soluble, or is that going to be a solid? I mean, is it going to be a precipitate, or is it going to be soluble? Insoluble or soluble?
Soluble?
It's going to be soluble, so we're going to put aqueous around it.
Is next to H2O, is it an L?
That's an L, yeah.
Cool.
Does it look like a D?
I don't know what it looked like.
Oops. Yeah, oops. Yeah, that's an L.
Okay.
It won't let me fix it without erasing everything. So. Okay, questions? Concerns? Cash? Credit? Okay, so far we've talked about what type of reaction.
Acid-base reaction.
We talked about acid-base reactions, which is also the same thing as a neutralization reaction. What else?
Did we go over precipitation reactions?
So what are precipitation
Yeah,
reactions?
I don't remember.
There's another name for them.
Oh,
I
it's
like calling
double
them
displacement.
double displacement, yes. Okay, and then what was the other one that we started with? Fire.
What are they called? Oh,
Burn, baby, burn. Okay, definitely putting that one on the test.
Which one?
You don't remember?
I came in late. Did you go over something?
No, we've been going over for the last couple of weeks.
Oh.
Combustion reactions.
Combustion reactions, that's right.
Oh.
Took me a while to find it.
So you should be able to identify the types of reactions, right? And predict the outcomes.
Is that just predict, just kind of guessing what the form is going to be left in?
It's not guessing, because you should use your knowledge, the stuff that you've learned along the way. If you know you have two ionic compounds, they're going to probably form one is going to form a precipitate, and one is going to be soluble, right? Or in an aqueous solution. So if you know that, oh, that's an ionic compound, but that means you got to recognize it as an ionic compound.
Yeah.
So what is some of the characteristics of an ionic compound?
It's is it two metals?
Nope. If it's two metals, that's what type of bond?
Covalent?
Two metals is covalent?
No, I don't know.
Are you sure? Anybody want to help him out with that? What are two metals?
Ionic.
We haven't gone over bonding, huh? Let me go over bonding real quick. This is a quick rundown. So if you have two metals, it's going to form a metallic bond.
Okay.
If we have a metal and a non-metal, it's going to form what? And I'm pretty sure we talked about that, because didn't we talk about electron delocalization?
I think so, but I mean, I was just kind of brain farting.
Okay. So if I have a metal and a non-metal, what type of reaction is, what type of compound is that going to be?
Ionic.
It's going to be an ionic, right? So metal and non-metal, ionic. If I have all non-metals, it's going to be
Covalent?
covalent.
Okay, yeah.
Yeah. And think about it. Remember I told you, I'm sure I told you about this.
Yeah.
So you're not going to steal from somebody across the way, because ionic is giving and taking. So you're taking something, right? So that's an ionic exchange. One takes and one is giving. So you're not going to take away from your neighbor, right? Did I tell you that?
Yeah, okay.
So you want to try to remember that.
Okay, gotcha.
Okay. So, are you ready for the next one?
Yep.
The next one we're going to talk about is redox reactions. So redox reactions are, let me explain it. So electrons are constantly moving, right? And so the way these reactions actually occur is because you have electrons that are going to be either given up or taken, right? So for instance, we have sodium metal and chlorine gas. So in this case, sodium metal is going to be giving up those two electrons because it wants to be like who? What does it want to be like? Erica.
I was gonna say noble gas.
Noble gas. Good answer. Good answer. Okay, so it wants to be like a noble gas, so it's going to want to give up those two, in this case, since there's two of them, 2 electrons. Now the chlorine gas wants to be like whom? Alexis.
The noble gases.
A noble gas, right?
Yeah.
Simple answer. Everybody wants to be like the noble gases. Come on. I know it's not Monday. This is Tuesday. You guys should be jumping, right?
Yeah.
Okay, so we need you guys jumping. We need you excited about this. Now, since they're both wanting to be like the noble gases, chlorine is going to want to get 2 electrons so that each of those chlorine could be negative, right? So they're going to broker a deal, right? So this guy's going to kind of give it up. So these are what we call half reactions. In this case, this guy we know is going to be giving up 2 electrons. In this case, we know that this guy is going to be needing 2 electrons to reach its goal, okay? So let me give you my little secretness. So if you're gaining an electron, then you're going to be reducing, right? Or reduction. If you're losing, you're going to be oxidizing or oxidation, okay? Oops. God damn it. I hate this. It's not behaving for me. Okay, so losing an electron, and so how I remember it, you can remember it any way you want to, but I always say Leo. Leo, loss of electron, oxidation, and gain of electron. Okay, so which one is being oxidized and which one is being reduced? Looking at the half reactions.
The one that's reduced is being oxidized.
Which one is which of these two reactions? That's what I'm asking you. Now don't try to put circles around me there, Alexis.
What do you mean?
The one that's being oxidized is being reduced, right?
Yes.
In a real equation, you're always going to have both of them occurring. Somebody's going to be being oxidized and the other guy's going to be being reduced. So here we actually break them up into half reactions. One is the oxidation reaction and one is the reduction reaction. So that's why we call it oxidation-reduction reactions. Okay, so which one is gaining an electron? Which reaction represents gaining of electron?
The chlorine.
Chlorine too?
The chlorine, right? Because guess what? It's plus 2 electrons. That means you're gaining electrons, right? So the chlorine gas is going to be the reaction where a chlorine gas goes to the chlorine ion. That is going to be your reduction reaction. Let's see. And then by default, which one is losing an electron?
The sodium.
The sodium. So as the sodium metal is going to sodium ion, it's losing an electron. You see? Electrons are being lost here. Okay? Simple. Now it's not brain surgery.
Example?
Another
So-
example?
Yeah,
Okay.
just to see how we'd work it out.
Okay, so let's give you another one. We'll go. Okay, so that's your reactions. But can you tell me the two components that are going to make this happen? So what are the two half reactions? Here, let's put this on the whiteboard. You don't mind, do you?
No.
Okay. Okay, so can you help me figure out the two half reactions?
So we'd start off with the 2mg. So we always split both reactions, right?
That is the easiest way to do it. I'll show you another way a little bit later.
Okay.
And then what is that going to make? What is going to be the product of that half reaction?
Um, 2mg 2 plus or no?
What ion is it going to form?
It's Mg2 plus.
Oh.
Because if it's going to be like a noble gas,
2 plus 2 electrons.
is it 2 electrons or is it 4 electrons?
4 electrons.
So that's just because there's 2 mg's, right?
Yep.
Okay.
Okay. Now what about the other half reaction?
You'd add the 4 electrons to the other one or no?
Okay.
So it'd be O2 plus 4, 4 E minus, yeah.
Okay. And that's going to make
2O2.
okay. And then we know when these guys come together, what's going to happen. Oh, baby, I love you. All right.
Gonna reproduce.
Yeah. They're going to reproduce. No, they're going to join, right? They're going to be attached at the hip. Okay. So this is just showing you oxidation reduction reactions. Now, can you identify which one is being oxidized and which one is being reduced?
The magnesium is oxidized. And
Which one?
the magnesium is oxidized.
I still didn't hear you clearly. So we'll do it like this, A or B? Reaction A or B? Which one is the oxidation reaction?
A.
A? Okay. Now, which one is B is the reduction reaction?
B.
B.
And how did you determine that?
Because one is gaining electrons.
Yep,
the other
so
one-
this guy is gaining electrons. So that's gain of electrons, reduction. And the other guy is
Losing.
losing electrons. So again, not brain surgery.
No.
Good, good, good. Okay. So when you're talking about the metal is being oxidized and the gas is being reduced in both of those cases. Okay? Okay. Now, oxidizing and reducing reagents are kind of switched, right? So we knew that the metal was being oxidized, right?
Mm-hmm.
Okay.
Yeah.
So, but then what we would say is the metal, sodium, is our reducing reagent. It's causing the other guy to do that opposite, right? So it's causing the other guy to gain electrons. So sodium metal function as a reducing agent. It's having an effect on the other thing, okay? And then the chlorine gas function as an oxidizing reagent. It causes the other guy to lose electrons. Do you guys see that?
Yeah.
Yeah.
Okay, so that's redox. Okay, pretty simple.
Yeah.
Okay, so let's add a little more to it. Now, when you're talking about covalent things, we have to provide what we call the oxidation number. Okay, and there are going to be some rules to remember. Okay, so anytime that you're working with an element itself is going to have an oxidation number of 0. Okay, so let me write these down. And there's kind of a hierarchy to the rule as well. Okay, so an element oxidation number is always going to be 0. Okay, so what are these guys? Are these guys elements, or are they molecules? Or are they, what are they?
Atomic.
They're diatomic elements. So their oxidation number is going to be
0.
0. So both of these guys, their oxidation number is going to start off at 0. Okay, so when you have a compound formed, hydrogen has 2 options. It can have a +1 or it can have a -1. 90% of the time, hydrogen is going to prefer a +1 oxidation. So this guy is going to have a +1. Now, your halides are going to have a -1. Okay? So let me add this to our little list. Get it? Now, these are oxidation numbers. They're not necessarily the charges associated with it. This allows us to understand what's happening with those bonds and how they're interacting, okay? Oh, and the oxidation number of an ion, let's say sodium plus, is always going to be the charge on that ion. So we'll look at 1, 2. And that's on a monoatomic ion. So let me be specific on that. Okay, so then this guy here is going to have a -1. So who's being oxidized? If I'm going from 0 to -1, that means it's gaining an electron. Who's being oxidized? And then if this guy is going from 0 to +1.
Chlorine.
Chlorine.
Being
Okay.
oxidized.
So you said chlorine is being oxidized?
Yeah.
Hydrogen?
Hydrogen. Who said that?
Me?
Who's me?
Selena? Me?
Selena. Okay, Selena, that is correct. So because you're going from 0, if you think about it, 0 to +1, is that losing an electron or is that gaining an electron? If you're going from a 0 charge to a +1 charge,
Is that gaining?
It's
Losing
losing.
electrons.
Oh,
it's losing an electron, right? Because if we have a negative, right, we're adding an electron. Electron is negative. So if I'm going from 0 to a -1, am I gaining an electron or am I losing an electron?
you'd be gaining?
I'll be gaining, okay? So if we did these half reactions, we'd have H2G is going to be yielding and then Cl2 plus 2 okay? So if you add the two reactions together, they should cancel out the electrons, and then you'll end up with your product. So these guys will come together, okay? Are you with me? Or are you like, I have no idea what the hell you're talking about?
With you a little bit.
Okay, a little bit. Okay, so remember these rules so far. So we have elements have the oxidation number of 0, and then monatomic ions have the oxidation number equal to that charge. So those are your first two rules. Okay? Oops, got carried away. So let's go clear. Our next, oops. I am not, things are not working for me today. Okay, so let me rewrite these rules. You mind if I just write ox number?
Yeah.
Okay. I'm gonna do this just in case I delete it again. Okay. So our next two rules, as I told you, we had hydrogen. Yeah. Hydrogen can be a +1, can be a +1 with nonmetals, and a -1 with metals. Okay, so if we have Okay, so then in this case, hydrogen is going to go from, so this is an element, and this is an element. So what are the oxidation numbers?
0.
And this guy's oxidation number?
0.
0. Okay, so over here, what is this guy's oxidation number going to be?
+1.
And then the hydrogen?
-1.
Okay, so if we go from 0 for hydrogen to -1, is that oxidation or reduction?
Reduction.
And then if I'm going from 0, let's do this, 0 to +1,
Oxidation.
are you with me, Raphael?
Yeah, I'm just wondering, how come the oxidation numbers on the left side on the reactants are 0 comparison to, is it because after the reaction?
No, they're 0 because we know that the oxidation of all elements, are these not elements?
Yeah.
Sodium, it's an element. This is the natural state of hydrogen gas. It's an element. So it's always going to start off at 0.
Okay.
Okay?
Yeah, okay, I got you. Thanks.
Okay.
Dr. Henry, I have a question.
Yep.
Is there like priority in some of the compounds, or is there always a strict set of rules for the elements?
It is priority, but it's a hierarchy. So element is number 1, right? That's why we list that first. That rule comes first because that's the most important rule. Second important rule is monatomic ions have the oxidation number equal to their charge. Okay? So if you have Cl minus,
Okay.
then
Yeah.
it's going to have a -1 oxidation number. Okay? Now in compounds,
Okay. Yeah.
now these are the ones that it's going to get a little hairy here. So we have oxygen. So it's going to almost, or say in most compounds, have a -2 oxidation number. Although, if you have a peroxide, oxygen can sometimes be -1, and that's for a peroxide, which we know is, write this. I can do it. Come on, there we go. Which is, it's 2 O2 2 minus. So that means each one has a -1 charge. And rarely, very rarely, oxygen will be crazy. We'll have a -1/2. oxidation number. And then this is in the case of superoxides. Which is, I'm running out of room. Oops. This thing is so crazy. Okay. Okay. So you with me so far?
Yeah.
So
Wait, so like if you had like, for instance, ammonium hydroxide, how would you split that up?
ammonium.
Yeah, like if you had ammonium hydroxide together,
hold
like
on.
how would you go about splitting that?
Okay, so let's go ahead and write it. So just for the record, this is a decomposition reaction.
Okay.
Okay, so in this case, right, let's make sure it's balanced. Yeah. Okay. So what is the rule for oxygen? I mean hydrogen?
For hydrogen,
Mhm.
that it's a +1 with nonmetals.
Okay, +1. So then over here,
Would that be +1 too?
that's going to be +1 too. Okay, what about oxygen?
Oxygen. Is it 2 minus or minus
Okay.
2?
Okay, and in the case of nitrogen,
And then
now
nitrogen.
let me give you a hint. The charges all have to add up at the end.
Okay.
So
So
if this is also a +1, and we have 4 of these guys, so then what does nitrogen have to be?
Does that have to be -4 minus or -4?
Is
So
minus
if
3.
this is +4, this is -2, and this is +1. So then this has to be, did you say -3?
Yeah, minus 3.
Yeah. Okay, and then the same thing over here. This guy would have to be -3. So in this case, nothing is being oxidized or reduced. They're keeping the same structure. Right, so nothing had to be exchanged. This is something that's just going to happen naturally.
Oh, okay.
Okay.
Yeah. So all of those charges add up to 0?
Yeah, so it has to add up to 0 because each one of your hydrogens are a +1, right? And then over here, each one of your hydrogens are a +1. This guy is a +1 as well. So at the end of the day, this guy, all of these guys have to add up to 0. We have 2 hydrogens, we have 1 oxygen. That adds up to 0. You have -3 for your nitrogen, and you have 3 hydrogens. All of them are +1, so that adds up to 0.
Okay.
Okay. So
Yeah.
don't worry, we'll get more, and then you'll see where you're actually exchanging. Okay, so let's add on to our table here. So So we have your halides. So fluorine is always going to have a -1. And then all your other guys are going to have a -1, except when they're with hydrogens or other, so let's go, other halogens are also going to be a -1. Except when with oxygen and other halides, or sorry, other halogens that are higher. Okay. So, and then the last major one is your polyatomic ion has to add up to charge. Okay, and all, let's see, polyatomic ions and molecules. Okay, so those are the basic rules. So let's see if we can give you clear. Damn it. Damn it, I did it again. All that work. And it won't let me get it back. Oh, I hate Zoom now. It used to work. Okay, so did you guys get the 10 rules?
I didn't get the last one.
Okay, so the last one was, and I'll type them up again eventually, but we'll work through a problem first. Okay, so the last one was all molecules or polyatomic ions have to add up to charge. So if the molecule has a 0 charge overall, so what does the charge have to add up to? And that's the 10th rule. Somebody has it. Okay, so Sean asked, he says, for rule number 9, what do I mean by a higher halide or a halogen? So what I mean is higher on the periodic table, right? So fluorine is the highest, chlorine, then bromine. Make sure I'm not lying to you.
Chlorine,
Chlorine.
then bromine.
Yeah, so fluorine, chlorine, bromine, iodine. Okay, so iodine, if you have chlorine and iodine, chlorine is going to have the minus charge, -1 charge, and iodine is going to be left with whatever's left over. Okay, so let's start off with this guy. So based upon the rules, what is going to be the oxidation number for hydrogen? for each of the hydrogens.
+1.
So +1. Okay, and there's 2 of them. So then what is the oxidation number for sulfur?
Negative.
Negative? Would it -1 or remember there's 2 of these guys. It'll be -2. That's right.
We have to cancel out, right?
That's right.
Okay.
Because at the end of the day, it has to equal 0. Okay, so what about this guy? So what is the oxidation number for oxygen?
-2.
So each one is -2. Okay, and I have 4 of them. So I have 4 times -2.
8.
So that equals -8. So then sulfur has to be, if I wanted to equal, remember it has to equal the charge on that ion. So
Positive
it has
8.
to equal -2. So it has to be what?
Oh,
Positive
Be
6.
6. Okay, so then the oxidation number for this sulfur is 6. Okay, do you guys get that?
Yeah.
So when there's a charge, we need to add it to be the charge.
Yep, that's right. That was that. Rule number 10 says all molecules and polyatomic ion have to add to the charge.
Okay.
Meaning that it has to add up to the charge. Let me fix that. That makes sense. Add up to the charge. Okay, so let's say we have this.
It's gonna be that's gonna be -2. A 1?
Okay, that's right. So your BR is going to be a 1, and then each your CLs are going to be
-2?
each one is going to be
I mean,
-2.
sorry. -1.
Yeah, -1, and so 2 of those, both -1, so that should add to them. Okay, so that, does that give you an example, Sean?
Yeah.
Okay, and so that was the 9th rule, right?
It's gonna be or -1 too? Or
What was that?
it's gonna be or -1 as well?
Nope, because Br is lower on the totem pole, right? So chlorine will get its -1, and if chlorine is -1, and this charge is -1, so each one of those, we have 2 times -1. And we'll put, say, Y for whatever the charge is bromine. So 2 times -1, and that's a times, not a X, times -1, let's just do it right. And we want it to equal a -1. So what does Y have to be?
+1. Wait,
+1, right?
Yeah.
Okay, so that means that your bromine has to be 1. Are you clear?
Yeah.
Okay. So what about, what about this guy?
PL is -1, O is -2, and P is +3.
If it's CL is -1, O is -2, so then P must be
3.
-2.
+3. That's right. Yeah. Piece of cake?
So.
Balthazar, are you getting it?
Yeah. Or just so or first or first one should always be a positive.
Not necessarily. It just depends on what the other oxidation numbers are.
Oh, okay.
And cheapen off.
What was that? So so you know that oxygen is always going to be -2, except under special circumstances.
Yeah.
Okay, so oxygen is going to be -2. You know, chlorine
-1.
is, except for when oxygen is around and it has no choice, chlorine is going to be a -1. But if there's something else around that can take the burden, chlorine is going to make sure that it's -1, and then whatever's left gets to carry the burden. Right? So what if we had something like this? Okay, so what is the oxidation number for oxygen?
-2.
Okay, chlorine,
-1.
-1.
-1 for each one. Okay, and the hydrogen,
+1.
1.
so then 4. So then what would be the oxidation number for the phosphorus?
+3.
Okay, so we have 2 -1s, so that's altogether -4. We have +1, so that makes it -3, so we need to have a +3 to balance it out. Piece of cake?
Yeah. So pretty much finding out the ones that you know first, I guess.
That's right.
Okay.
And pretty much what we're trying to do is to balance the equation, right? To balance the ones on top.
Yep, you want to try to balance it so it equals the charge that is on that molecule. So this guy has a 0 charge, so we want to make sure that at the end of the day, with all of the ones that we have in there, it balances out. Okay.
No.
So what about this? Let's do this guy, and then we'll move on. Okay.
O is negative 2.
Judy says 6.
Would it be +7?
It's positive 7. Okay, so we have
-2
5 times negative 2.
equals -10.
So that equals negative 10. So for us to have, so you said positive 7. That is correct.
Um,
Oh, yay.
Good job.
good job.
Thank you.
Okay, questions, concerns? Cash?
I don't know simple math, that's for sure.
Okay, I'm going to erase it again, and this time I'm meaning to do it. Okay. Okay, so we already talked about redox, what it means and everything like that, right? So another way of looking at it, so it's an oxidation reaction if you're increasing the oxidation number, right? So that means electrons are being losing. So if you go from a negative to a positive, the oxidation number is increasing, okay? And then if I go from a positive to a negative, then that means it's being reduced, okay? So you guys want to test this out for the reaction?
Yeah.
Okay, so here, let's write the oxidation numbers for each one of the elements. Okay, so what would be the oxidation number here? And then you're going to tell me, is it being oxidized or is it being reduced?
Jesus.
So funny, we tried this, but not with, we weren't trying to make it solid rocket fuel. We were trying to do something else, so. Okay, so let's start off with the aluminum. Oxidation number for aluminum.
Would it be 0 because it's by itself?
It's 0, it's an element, that's right. Okay, so then let's come over here. It's with oxygen now. What is the oxidation number for oxygen?
-2.
-2. And we have 3 of them, so that's a total of -6. So then what must be the oxidation number for the aluminum?
6. Wait.
+3.
So each
Okay.
aluminum is +3. That's right.
Yeah. Okay.
Okay, what about here? So chlorine is what?
-2.
Chlorine is -2.
-1.
Oh,
Chlorine is -1. Okay, and we have 3 of them. So then what must be the oxidation number for the aluminum here?
+3.
+3.
+2.
Okay, so let's come over here. So we have 2 ions, right? So we have this ion and we have this ion, right? So we should probably break those up. So what is the oxidation number for the oxygen?
-2.
-2. So what is the charge on Cl04 minus? You guys remember? It's a polyatomic ion.
4? No.
It's called perchlorate.
Oh.
-1.
It's a -1 charge. So it has to add up to a -1 charge. So if we have 4 of these, 4 times -2, what must be chlorine then? For it to balance
+7.
out.
+7.
Okay. So chlorine is +7. Okay. Okay, so this guy is a +7. Okay, Now we know that ammonium has a +1 charge. And what is the rule for hydrogen? What is the charge on that hydrogen?
+1.
+1.
+1, and we have 4 of them. So then the nitrogen has to be
A -4.
is it -4? Because it's a +1 charge. Sorry. Got to put my plus there.
-3.
-3. Okay. So then we come over here. Our hydrogen is going to be
+1.
our oxygen is going to be
-2.
our nitrogen gas is going to be
0.
okay. So if we look at the nitrogen, we're going from a +3 to a 0. Is that going to be reduced or oxidized?
Reduce.
Guys,
Oxidize.
So you say oxidize. Are you sure?
Yes.
Yeah.
yeah.
Yeah,
Okay.
oxidize.
Loss of electrons, that's right. It's being oxidized. Okay, so we have aluminum. That is, let's use a different color. Aluminum that is going from 0 to a +3.
Oxidize.
Okay, so then we have okay. We have chlorine, which is going from a +7. That's a 7. This is a different color. We have a +7 to a -1.
Reduced.
Okay. Oxygen stays the same. Hydrogen stays the same. So are we good? We got everything covered? Piece of cake?
Yep.
Yeah? No, maybe?
Yeah.
Maybe.
No.
Getting easier.
Who said no? Anyone?
I said maybe.
You said maybe?
Yeah.
Okay. Do you want to try another one? It's an easier one.
No.
You guys can tell me. You said no, you don't want to try another one.
No, I would like to try another one. Let me redeem myself.
Okay. Okay. So in this case, copper. What is the oxidation number?
0.
Okay. The nitrate. So what it would be the oxidation number on the nitrogen in the nitrate? Because we know nitrate is NO3 minus.
Wait.
What did you say it was?
+5?
Okay,
+5.
good job. +5. Okay, because we know that each one of those are -2. So then the silver,
0.
0.
are you sure? The silver and the silver nitrate. So if
Oh.
this is a -1, this has to be what to balance it out?
Positive one?
Positive.
So if it's +1, so what would be the oxidation number for it?
+1.
+1. Okay. And that's a 2 for those who can't read my handwriting. Okay, so then over here, the copper is going to be there's 2 nitrates. It has 2 nitrates to balance it out. The copper is going to be what?
2 plus.
+2. Okay, the nitrogens are going to be the same as over here because you guys already calculated that. So that's +5. The oxygen is going to be the same. And the silver here,
0?
okay. So who's being oxidized and who's being reduced? So we're going from 0. We're going from 0 to +2.
Oxidized.
And I'm going from a +1 to 0.
Reduction.
Piece of cake? Much simpler equation, right?
Yes.
Yeah.
Okay. So single replacement reactions are an example of oxidation and reduction. So when you're going from that metal, right, and you're going into solution, and the metal is replacing one another, we know that that is an example of a redox reaction, right? One is becoming an ion, the other one is becoming back to the metal form, okay? Questions, concerns, Cash? Okay. And brings us to, I don't know, did I talk to you guys about the activity series? I think I did.
Yeah.
I gave you that table. I showed you the table.
Yeah.
See if I have it.
I think you covered it the last few minutes
You did?
of the last class.
Yeah. I showed you that table
Yeah.
or something like it. Yeah. Okay. Good, good. So I got ahead of myself. So you guys can see, if you guys have your table available, you have copper is above silver. So then copper can replace silver in that chemical reaction. Okay, questions, concerns, Cash? Okay, so another way that we can sit there and do it, we can sit there and balance out the equations, right? And get our half reactions. Now, the way that we would work these half reactions, right? And you're gonna see this again if you guys take 1B, you'll see it in a more complex way when we talk about redox. But sometimes reactions can be very difficult to determine and balance by just inspection. So the way that you would do it is you would break it up into half reactions. Although I hate the half reactions, but they do come in handy when you're trying to balance out or trying to understand what's going on, okay? So most redox reactions are going to be taking place in an aqueous solution or a medium with water, hydronium ion, and hydroxides. And so you're always going to have these guys as products to sit there and use to help balance out those reactions because they're aqueous. So that means you have abundance of those things available to work with, okay? So I'm going to go through the steps that how you would do it with these components, and then we'll try to do, we won't have enough time to do it. We'll start back on this on Thursday. How about that? Okay, since it's time for a break. Okay, so we'll have to take a break, and then you guys have lab. So what you're going to need for